On this RAM, P0073 means the ambient air temperature sensor circuit may be reading high electrically at the controller. In plain terms, the outside air temperature signal may be too high as an electrical value, not necessarily because the air temperature is actually high. The truck may still drive normally, but the outside temperature display may be wrong, and systems that use outside temperature information can be affected. The broad fault areas are the sensor and its connector, the signal circuit, the sensor return circuit, a short to voltage, an open or high resistance circuit, terminal problems, or a possible controller input issue after the circuit checks pass. Before getting deep into the circuit, start with the basic system checks. Look for applicable bulletins, case information, or flash updates. Check for battery voltage-related faults, and if other ambient temperature or communication faults are present, understand what they mean first. For an active fault, record all stored and active faults, capture the freeze frame data, and save a vehicle scan report in case you need to compare conditions later. Then review the captured conditions and the monitored and set conditions. Erase the faults, operate the vehicle or system under those same conditions, and see if P0073 comes back or the condition is still present. If it returns, continue with circuit testing. If it does not return, treat it like an intermittent and test accordingly instead of guessing. This is a 2-wire temperature sensor circuit using a 5.0-volt reference signal. In the general fault logic, a circuit high or open condition is above approximately 4.9 volts, and a circuit low condition is below approximately 0.10 volts. In the diagnostic fault logic, the same guideposts are above approximately 4.9 volts for high or open and below approximately 0.10 volts for low. The circuit low fault is typically in the 0.1 volt range, and the circuit high fault is typically in the 4.9 volt range. The sensor is usually at the front of the vehicle near the grille, but on some applications it can be in the driver's side mirror housing, so identify the actual sensor location and the module you are testing at before back probing. Also remember that circuit high and low faults are monitored by more than one controller, but only the PCM performs the rationality check on this ambient temperature signal. There are multiple valid test methods here, and you do not have to run every method. Choose the one that fits access, tooling, and the way the fault is failing. What you do not want to do is condemn a sensor or controller without checking the wiring and connector path. If P0073 is intermittent, back probe the temperature sensor signal circuit and connect the scope lead there. Watch circuit voltage while you wiggle test the harness. If you cannot keep eyes on the scope during the wiggle test, set a trigger so the scope catches the event. For this high circuit fault, set the trigger above 4.9 volts. If you are also watching for the low side during the same intermittent check, the low trigger is below 0.1 volts. The goal is to make the harness movement show you whether the signal is opening, going high, or being pulled somewhere it should not be. A good way to separate the sensor from the wiring and controller is to use the electrical test lead kit at the temperature sensor connector. Connect the kit to the temperature signal and sensor ground circuits, then move the switch between open and closed while watching the scan tool. In the open position, the high fault should set, and the signal should read 5.0 volts when switched to the open position. In the closed position, the circuit should be pulled low and read 0.0 volts when switched to the closed position. Then use the adjust position to vary resistance and watch whether the controller signal voltage responds. Match what you see to the correct result branch. If the fault's set as expected and the scan data moves from 5.0 volts to 0.0 volts, the controller and circuits are testing good. At that point, inspect the sensor connector closely for pushed out, spread, corroded, or dirty terminals before calling the sensor bad. If a resistance table is available, compare the sensor resistance to that table to confirm the sensor fault. The AAT sensor is individually serviceable, so if its measured resistance does not match the technical values, the sensor is the part being evaluated, not the whole mirror assembly. If the kit test does not behave correctly, use the result to aim the next check. If the signal is stuck low or only a circuit low type fault sets during the test, look for the temperature sensor signal circuit shorted to chassis ground or to the sensor ground circuit. If that circuit is not shorted, inspect the related harness connectors for terminal problems before condemning the controller. If no issues are found after that stuck low path, the controller is the most likely fault. If the signal is stuck high, or only the circuit high fault sets, think open circuit or very high resistance in either the signal circuit or the sensor ground circuit. To split those two, move the test lead from sensor ground to a good chassis ground while watching scan voltage. If the voltage drops to 0 volts, the resistance is in the sensor ground circuit. If voltage is still present, the resistance is in the signal circuit. Check the suspect circuit for high resistance. Typically, it should be less than 30 ohms. If those circuits check good, move on to connector checks and controller evaluation. Inspect the related connectors for pushed out, spread, corroded, or dirty terminals before condemning the controller. If no circuit or connector issue is found at the end of that path, controller replacement is allowed by the diagnostic path. If you are using a DVOM instead, first verify the temperature sensor and controller connectors are fully connected and locked. Turn the ignition on. Back probe the temperature sensor signal circuit at the sensor connector and measure the signal voltage. Match the measured voltage to the correct branch. If it is between 0, 1 and 4, 9 volts, the sensor signal is most likely giving a legitimate reading. If the fault is active but scan tool voltage does not match the DVOM voltage, the controller becomes suspect. If the signal is a constant 0 volts, use the active fault direction to decide whether you are chasing an open between the controller and sensor, a short to ground in the signal circuit, or possibly a sensor fault. If a sensor fault is possible in that branch, disconnect the sensor and watch for the high fault to become active. If the signal is above 6 volts, the signal circuit is shorted to another voltage supply. If the signal is constant 5 volts, look farther downstream for an open, most likely at the sensor or the sensor ground circuit. With the sensor and controller disconnected, check the signal circuit for high resistance and short to ground, and inspect every connector in the path before condemning the controller. To continue checking the sensor side, move the test lead over and back. Probe the temperature sensor ground circuit at the sensor connector. Even though P0073 is the circuit high fault we are focused on, your circuit checks can point you into the low fault side of the same two-wire circuit. With an active low side result, disconnect the temperature sensor connector while watching for the high fault to become active on the scan tool. If the high fault becomes active when the sensor is unplugged, the sensor is most likely faulty. If it does not become active, disconnect the controller connector to isolate the circuit. Then check the temperature signal circuit for continuity to both chassis ground and the sensor ground circuit. If there is continuity to either one, repair the signal circuit for a short to ground or to the sensor ground circuit. If the signal circuit is not shorted, controller replacement is only reached after that circuit isolation proves out. For an active circuit high fault, disconnect the temperature sensor and measure the signal circuit voltage with the ignition on. The signal circuit should be between 4, 9 and 5, 6 volts. If battery voltage is present, repair the sensor signal circuit for a short to another voltage supply. If the voltage is correct, move into the jumper test. Monitor the scan tool and jumper across the sensor connector terminals with the ignition on. Normally, the scan tool signal should drop to 0 volts on the scan tool with the jumper in place. If voltage data is not available, watch for the circuit low fault to set with the jumper installed. If either of those happens, the sensor is faulty. If the signal does not drop to 0 volts or the low fault does not set with the jumper installed, check resistance in the temperature sensor signal circuit and sensor ground circuit. Typically, circuit resistance should be less than 5 ohms. Repair any open or high resistance found. If both circuits test good and the signal is still high or only the high fault is present, inspect the related connectors for pushed out, spread, corroded, or dirty terminals before condemning the controller. Only if no circuit or connector issue is found does the path allow controller replacement. If the failure pattern calls for a performance or rationality style check, disconnect the temperature sensor connector and connect the electrical test kit leads to the sensor harness connector. Move the switch to open. The signal should read 5.0 volts and the high side fault should be active or pending. Then flip the switch closed. The signal should read 0 volts and the low side fault should be active or pending. If the scan tool responds that way in both positions, the wiring and controller are good and the sensor is likely faulty. If there is voltage present between 0 and 5.0 volts with the tool in the closed position, there is likely resistance in one of the circuits. To separate it, remove the test lead from the sensor ground circuit and connect it to a good chassis ground. If the signal changes to 0 volts, the resistance is in the sensor ground. If voltage is still present, the resistance is in the sensor signal circuit. Confirm the suspect circuit by isolating it and measuring resistance between the sensor and controller connectors. If the resistance measurement does not catch it, carefully inspect the connectors in that circuit path for spread, dirty, or corroded terminals. If the circuits check good, keep separating the fault between the sensor and the controller instead of guessing. When a temperature table is available, use it to verify the sensor and controller response. The sensor table is held to +/10%. Some useful points in that table are -40 degrees C/40 degrees F/345, 26 k ohms/ lowest possible temperature reading, -10 degrees C/14 degrees F/53. 38 k ohms/ logical temperature values, -5 degrees C/23 degrees F/40, 89 k ohms, 0 degrees C/32 degrees F/31, 56 k ohms, 5 degrees C/41 degrees F/24, 55 k ohms, 10 degrees C/50 degrees F/19, 24 k ohms, 15 degrees C/59 degrees F/15, 22 k ohms, 20 degrees C/68 degrees F/12, 13 k ohms, 25 degrees C/77 degrees F/9720 ohms, 30 degrees C/86 degrees F/7780 ohms, 35 degrees C/95 degrees F/6370 ohms, 40 degrees C/104 degrees F/5200 ohms, and 150 degrees C/302 degrees F/181 ohms/ highest possible temperature reading. With the test tool and adjust, connect an ohmmeter to the leads, dial the tool to a table resistance value. Connect both leads to the sensor connector with the ignition on, and watch the scan tool for the proper reading. You can also vary resistance with the tool while monitoring temperature or voltage on the scan tool. If the actual sensor temperature can be acquired or reasonably estimated, measure resistance across the sensor terminals and compare it to the table. If no table is available for the sensor being tested, connect the electrical test kit to the harness connector, switch to adjust, turn the ignition on, and slowly change resistance while watching scan data. If the temperature or voltage value changes as resistance is varied, that points toward the sensor being likely faulty. For controller verification, open and short the circuits while monitoring signal voltage and fault behavior. If the expected voltage readings or faults do not occur when opening and jumping the connector, and the circuits are not shorted or open, the controller is identified as faulty. Before condemning it, check all connectors in the circuit path for water intrusion, spread terminals, pushed out terminals, burnt terminals, or corrosion. Keep verification separate from the testing. For the performance monitor, the check can depend on the vehicle sitting after an 8-hour cold soak, with the compared temperature values above -64 degrees C, -83 degrees F. A rationality fault is typically looking for the ambient temperature signal to be not within 10 degrees C, 15 degrees C, 18 degrees F, 27 degrees F of the other engine temperature sensors. After a wiring repair, a sensor replacement, or disconnecting the BCM connector during testing to correct an active fault, The ambient temperature signal may not update until the vehicle is driven for a minimum of 5 minutes above 15 mph. After that, verify the repair and confirm P0073 stays gone. The takeaway is simple. Prove whether the high signal is coming from the sensor, the signal circuit, the ground side, a short to voltage, or the controller input before replacing anything. For more diagnostic training, visit Diagnostics.com.